5. So homeworks, a couple of those homeworks due Friday at 5. Bidding methods, apportionment stuff. And so on and so forth. Oh, there's Jefferson. There. So where we left off last time was Jefferson's method. And remember, basically, Jefferson's method hinges on finding the right divisor. And the quote, right divisor is the one that's going to make it work out in the end, where the lower modified quota ends up being the exact number of representatives that we want. So we divide by the correct divisor. We give everyone the number of representatives that matches the lower modified quota. And when we do that, magically the lower modified quota matches with the number of representatives that we want. Okay, not magically, but you guys get the idea. And on the test, on the homeworks, that right divisor, well, let me take a step back. That right divisor often is very hard to find. A lot of times it takes some guessing and checking things. So on the homework, on the test, I'll say use the divisor, which is 25 units from the standard divisor. Or use the divisor, which is 13.6 units away from the standard divisor. Right? Something of that nature. And so I'll kind of give it to you or give it a distance from the standard divisor. We did examples number 1 and number 2 last time. I'm going to do example 3 this time. So in example 3, we want 120 representatives. We have the same districts as we had in example 2, but now we want 120 representatives. What I'm going to do is I'm going to go back to that apportionment Excel document. That we used last time. And I'm just going to put the populations in it. All right. Now, just so we calculate, remember there's 10,078 people. I want to take that 10,078, divide it by 120. The standard divisor is about 83.98. So the standard divisor is 83.98. Okay. Notice how that meant the quota was 120 with when I count the decimals, but the lower quotas add up to 117. So I need that 117 in Jefferson's method to go up to 120. So we're gonna start reducing our divisor. Maybe I reduce it to 82. Oh, that was too far of a reduction. So maybe I increase that to 82.5. Oh, that gave me 119. So somewhere between 82 and 82.5. So 82 to 82.5. How about 82.25? Nah. It's got to be somewhere between 82.5 and 82.25. Notice how this would take a really long time. Oh, there you go. This would take a really long time doing this by hand. Okay. There is a formulaic way of finding which divisor, but it's really, really involved. It's a fairly hard calculation. So I essentially just guess and check on this table. And obviously, if you have a lower quota that's above the number of representatives that you want, you move in one direction. If it's below the number of representatives you want, you move in the other direction. All right. But there you go. If we make our divisor 82.35, then the number of representatives that District A is going to get is 31. The number of representatives District B is going to get is 8. The number of representatives District C gets is 24. D will get 47. E will get 7. F will get 3. Does that make sense? So sometimes, again, this divisor can be really, really hard to find. You have to do a lot of different iterations and trials. That's going to be avoided on the test by just giving you how far away from the standard divisor it is. Like I said, the standard divisor was 83.98. So I'd say something like use a divisor that's 1.63 away from the standard divisor. Does that make sense? So that's Jefferson's method. In Jefferson's method, the number of representatives is simply just the lower quota once I've got the right divisor. And the right divisor means that the lower quotas add up to exactly how many representatives that I want. Is that right? Now, in example 4, I'll do this fairly quickly, but this is a 5-district example where I want to have 100 representatives represent the 5 districts. Okay, and I'm going to copy this table onto a Word document like we've been doing. Okay. So if I want 100 representatives, that means that if you added these populations up, it's 100,000. Okay, so the total population is 100,000. I think I want to make everything a little bit bigger. 1 point font. Go. So 100 representatives, population 100,000. That means the standard divisor would be 1,000, which again, remember, that essentially just means every 1,000 people should get their own representative. Okay. Now, let's do Jefferson's method on this. And obviously, we're not going to use the standard divisor, but that's a good place to start, and then we'll start lowering it until we kind of fit. So there's my population. There we go. Oh, I don't know why that's formatted different. I copied and pasted it, kept the formatting. Oh well. Normal. Sorry. So there we go. Standard divisor, like I said, starts at 1,000. 1,000 doesn't get me enough representatives with the lower quotas. So I start lowering it. Let's go to 975. Boom, 975 works perfectly. All right. So we use a divisor of 975. When I use that divisor of 975, I would take each population, 48,987, and divide it by 975. That gives me a modified quota of 50.24. So in Jefferson's method, that gives me 50 representatives. For B, divide 6,144 by 975, you get 6.30. That means give B 6 representatives. $7.42 or 3. Give 7 representatives to C. Give 21 representatives to D. And give 16 representatives to E. Now, here's the weird thing that's happened. Let me point it out. In District A, if we had done Hamilton's method, that was the previous method where, you know, we give everyone the lower quota using the standard divisor, and then the biggest decimals remaining get extras. If we would have done Hamilton's method, A would have received 48 or 49 representatives. You see that? In other words, if you look at A, they have over 48,000, but under 49,000 people. If each representative should represent about 1,000 people, that means A should have received either 48 or 49 representatives. That makes sense? Same thing with B. B should have received either 6 or 7 representatives. C should have gotten either between 7 and 8 representatives, according to logic, right? Since each representative should represent about 1,000 people, that's what should happen. A should get either 48 or 49, depending on the rounding. But they don't. They actually get an extra representative beyond what they actually deserve using the standard divisor. Okay. Does that make sense? So using the standard divisor and basic logic about what the standard divisor actually means, A is getting, quote, too many, unquote, representatives using Jefferson's method. And what this is, it's something called a quota rules violation or quota rule violation. If a district receives more than their upper quota or less than their lower quota with the standard divisor, then what we have is what's called a quota rule violation. And that's what happened to A. They received more than their upper quota with the standard divisor. You can also receive less than the lower quota with the standard divisor too. That's a quota rule violation as well. And it turns out, because we didn't use the standard divisor, we do get these quota rule violations with Jefferson's method. Right? So Jefferson's method can produce quota rule violations. By the way, Hamilton's cannot, because Hamilton's, we use the standard divisor, and you either get the lower quota or you add one, and that's the upper quota. So Hamilton's does not have a quota rule violation, but Jefferson's does. Okay. Does that work? Does that make sense? So while Jefferson's method doesn't allow for the Alabama paradox can't happen in Jefferson's method. The new states paradox can't happen in Jefferson's method. The population paradox cannot happen in Jefferson's method. A quota rule violation can happen, and that can't happen in Hamilton. Right? So there's kind of 3 issues that could happen with Hamilton's, one big issue that could happen with Jefferson's. Now you might say, well, which is worse? Quota rule violation or Alabama paradox, new states paradox, population paradox? And the answer is, it's kind of anybody's opinion, right? Both of these methods, both Hamilton's and Jefferson's, have these weird things going on. but that doesn't make necessarily one better than the other, or one worse than the other. Right? It's just kind of a subjective opinion for which one is best to use. And I think I said this last time, but you can imagine that with Hamilton's method, Hamilton was famously out of New York. Hamilton's method advantaged New York at one time in history. Whereas Jefferson's method advantaged Virginia at one time in history, right? That's where Jefferson was from. So, interesting stuff. Now, because of their close connection with Jefferson's method, I also, as a bonus, want to give you what happens with Adams's method and Webster's method. I'm not going to do a lot of examples here because they're very, very close to what Jefferson's method does, except they round differently. So Adam's method of apportionment is going to look like Jefferson's method. We're going to pick a right divisor. We're going to divide each district's population by that right divisor and get modified quotas. Instead of giving everyone the lower modified quota, like we round down every time, what we do with Adams's method is we round up every time. You move it up to the next whole number or the next integer, depending on what you want to say there. Whole numbers and integers. Whole numbers are positive integers. So, does that make sense? So basically, instead of rounding down, you just round up. But you do it with a modified divisor. Now, this modified divisor is not going to be the same one with Jefferson's, obviously. Because with Jefferson's, if you rounded everything up, we'd get too many. You use the same divisor and round it up, you get too many representatives. So this is going to be obviously a different divisor than what we used in Jefferson's and what we used in Hamilton's. All right. So let's go back to our standard example here. Oh, and I forget the divisor I should use. Dang it. So this is our example that we've done in all of our methods. So we've done it in Hamilton's method, then we did it in Jefferson's method. 38,343 for District A, 21,230 for District B, 4,899 for District C. D has 20,405. E has 15,123. Now, because I forgot which divisor I want to use, I'm going to go ahead and type that into my Excel sheet. So 38,343 goes in for A, 21,230 goes in for B, 4,899 goes in for C, 20,405 goes in for B, E goes 15,123. And sure enough, we get 100,000, we knew that. We know that the standard divisor is 1,000. We're not using the lower quota anymore. Now, this is the one where we want to use the upper quota. Everybody get that? Using the upper quota. And the upper quota is just go up to the next whole number. So if we were at 38.343, we'd round it up to 39. Now, obviously, this gives me too many representatives with my upper quota. So we're gonna increase the divisor in this case from the standard divisor. Maybe I increase it by 25. It's a little bit too much. All right, there you go. Increase your standard divisor by 20 in this case. And when you increase your standard divisor by 20, this becomes your representative allocation. Everybody see that? So, did I do that one? Yeah. Let me just fill out the table. So we have that. So we use our divisor of 1020. I take 38,343 divided by 1020. That gives me 37.59. So the number of representatives that we're going to go to is 38. 21,230 divided by 1020 becomes 20.81. So we're going to round that to 21. We're going to move it up to 21. 4899 divided by 1020 gives me 4.80. Move that up to 5. 2405 divided by 1020 gives me 20.005, which I have to move up to 21. Okay. And then 15,123 divided by 1020 is 14.83. I gotta move that one up to 15. And that's my allocation. Does that make sense? The only reason I went out to 3 decimal places here is that we can see it's slightly above 20. All right. And therefore we have to move it up. Everyone okay with that? Makes sense? Makes sense. So that's Adam's method. Adam's method is find a divisor where the upper quota will give you the number of representatives that we want. Now, Webster's method, by the way, Adams's method is named after John Adams, okay, who's from Massachusetts, right? And so you can imagine that Adams' method probably advantaged Massachusetts at one point in time, right? Let's do another one. Let's do what's called Webster's method, named after politician Daniel Webster. Not named after me, sadly, right? Okay. So Webster's method is very similar to Adams' method, very similar to Jefferson's method. We're going to pick a right divisor. But this time, instead of using either the upper quota or the lower quota, we're going to use standard rounding. So 0.5 and above will round up, and 0.49 and below will round down. So Webster's method is figure out a correct divisor and then do standard rounding. So let's do that same example, but now with Webster's method. Okay, same example, but with Webster's method. Now, what you'll notice, here I have standard rounding, right, over there. If I just put in the standard divisor, you'll notice that standard rounding gets me closer to the number of representatives that I want than the lower quota or the upper quota did. Okay. So the advantage of Webster's method is that the divisor tends to stay closer to the standard divisor. Does that make sense? So usually between Jefferson's and Adams and Webster's method, the tendency is that Webster's method stays closer to the standard divisor. So let's take 990, see if that works. Oh, that's too much. So somewhere between 990 and 1,000. How about 995? Oh. Put down 992. Oh, I already did that? I went the wrong way. Somewhere between 995 and 996. How about 995.5 with their divisor? There you go. That makes sense? So 995.5 is the divisor that we want. Now let me copy and paste this. Let's just do it that way. 995.5. So take our population. $38,343 divided by 995.5. I get 38.52. Now standard rounding would round that up to 39. Right? 0.52 is above 0.5, so 0.5 and above rounds up. 21,230 divided by 995.5 is 21.32 or 33. That's decimal is below 0.5, so we keep it at 21. 4899 divided by 995.5 gives me 4.92. That's obviously has a decimal above 0.5, so it's going to round up to 5. 2405 divided by 995.5 gives me 20.497. That is just below 20.5, right? So we keep it 20. And then 15,123 divided by 995.5 becomes 15.19-ish. And that gives me 15, right, with standard rounding. I went to 3 decimals here because if I went to 2 decimals, it looked like 20.5. And I want just to make sure that everybody sees that that decimal is under 0.5, right? So that's why I went out to 3 there. But you can see that the representatives allocation is this way. And because our divisor sticks at pretty close to the standard divisor, while you can get quota rule violations in Webster's, they're slightly less likely than with Adams's and with Jefferson's. All right. So Adams's, that's the one we did here. I should say Adams. Gave us this allocation. By the way, notice this allocation is different than Webster's. In Webster's method, D had 20 representatives, and I believe A had 39 representatives. See that? So between Adams's method and Webster's method, A and D swap. And if these states were Massachusetts and Virginia, or Pennsylvania and Virginia, or Pennsylvania and Massachusetts, you might see and realize why John Adams from Massachusetts wanted a certain method, and Thomas Jefferson from Virginia wanted a different method, and where Alexander Hamilton from New York wanted a different method, right? They maximize their states voting block anyways. All right. So what I was saying there is that both Adams and Webster's method, along with Jefferson's method, could have quota rule violations. But Webster's method is probably, out of those 3, the least likely, because Webster's method sticks closer to the standard divisor. Does that make sense? So because we stick closer to the standard divisor, usually Webster's method doesn't have isn't as likely. It's possible, but not as likely. Any questions about that? So Adams, Jefferson's, Webster's, they all have quota rule violations. Hamilton's have those 3 weird paradoxes that could happen. Okay. New states paradox, population paradox, and the Alabama paradox. Feel free to use that Excel sheet if you want when you're filling out things. This can help you with Hamilton's method as well, right? You give everyone the lower quota, you see how many representatives, and then you give extra, right, for the biggest decimals. So as long as you can see the decimals, you'll be good to go. But all right. As far as apportionment goes, which one do you think the U.S. uses now? The answer to that is the U.S. currently doesn't use any of these 4. It uses a very, it's almost too complex for me anyways. It's a very complicated system that is more involved than these 4. These are sort of, I would say, the first 4 attempts at apportionment. But then the mathematicians got a hold of it. they've kind of adjusted it. So it's kind of a hybrid system in some senses, but it's more involved. It's a more involved calculation. All right. I kind of like the easier calculations, to be honest. I think people can make more sense, and it doesn't look like there's any shenanigans going on. Everybody can replicate it, basically. But that's not what we use. We use some convoluted calculation type system. And that's in part because we have to give every state, all 50 states, at least one representative, so on and so forth. All right. Any questions? No? All right, so speaking of systems in the United States and how all that kind of stuff works, we're then going to move on to the next chapter. Last chapter was fair division. How do you fairly allocate things? Now we're looking at voting, which is also kind of about fairness in a lot of realms. So once we've allocated representatives, we have to vote for those representatives, right? And it turns out there's a lot of different systems of voting. Okay. And it's not necessarily about fair share, but we do want a fair system. A fair system means both that it's fair to the voters and that it's fair to the candidates. Now, we'll see later on systems where not everyone has an equal vote. And you might think, well, wait a second. We're so used to voting, meaning voting for our representatives in government. But voting can mean a lot of things. Voting could also mean I vote for the CEO of a company I own stock in. And if I own 1,000 shares of stock and somebody else owns 1 share of stock, we probably shouldn't have the same votes. Does that make sense? So if I own 2 shares of Walmart stock, but Warren Buffett owns 20,000 shares of Walmart stock, then he gets 20,000 votes and I get 2 votes. Does that make sense? So that's kind of where that comes from. So sometimes we don't always want to have an equal vote, but we are going to start out with equal votes. We're going to start out where we're voting for like a representative and everyone gets an equal vote. All right. Now, the easy situation is when we have 2 candidates running for the same spot. If we have 2 candidates, then what we do is we use what's called majority rule. Every voter is going to get a single vote, and they can either vote for candidate A or they can vote for candidate B. Once it's all said and done, whichever candidate has the most votes wins. It's a pretty easy system, right? So we only have 2 choices, and everyone everyone gets one vote, they can choose A or B. By the way, this doesn't always have to be representatives. Like I said, oftentimes we vote on things that are not representatives. So when we live in Michigan, proposals come on a ballot. So there's a proposal 1, there's a proposal 2, there's a proposal 3, and a proposal 4 last big voting cycle, okay? And when you voted on those proposals, you got to vote yes or no. Basically, adopt this proposal or don't adopt this proposal. When they legalize marijuana, you can vote yes or no on it. Okay. And if you got more yeses than no's, then the proposal went through. If you got more no's than yeses, then the proposal stopped. So we do use majority rule quite often, especially on things like proposals. Or there's a proposal in our district to have mid be the college, the community college for the Gratiot Isabella RSED, right? And so that was a yes/no vote again. Now, majority rule, when you only have 2 options, is a great system. It has a lot, in fact, all of the real desirable properties that we want in order to treat things fairly. If we have only 2 representatives, then they're treated the same. You know, everybody gets a choice on 2. All voters are treated the same. Every vote counts the same. And here's the other one. If I'm a voter and I had voted for the losing candidate, if I wanted to switch my vote, the result stays the same. All right. So if you have only 2 options and you voted for a losing candidate, switching your vote around does not change the vote. So if you're a voter who voted for the losing candidate, yes, you may feel sorry that you lost, that it didn't go your way, but there's no thought in your head that if I would have switched, the result could have came out different. Does that make sense? So, yes, my vote, I didn't get it the way I wanted, but if I would switch my vote, the result would have stayed the same. Okay? And that's a big advantage compared to what we're going to see in the future. It turns out majority rule with 2 candidates is the only system that satisfies all 3 of those things. Majority rule with 2 candidates is the only system that satisfies all 3 of those properties. This result is known as what's called May's theorem. May is the last name of a person. that this is named after. But May's theorem says if you want all voters treated the same, if you want all candidates treated the same, and if you want this other property that if a losing voter switches their vote, the result stays the same. The only system that actually has that is majority rule with 2 candidates. Majority rule with 2 options. Every other system violates one of those. And mostly it's the third property there. Okay. Now, if you think about that third property, why that's nice is because I don't tend to game the system in that regard. If I am a voter and I know that switching my vote away from a loser doesn't change the result, then I'm free to vote for that loser. And I don't need to second guess myself. I don't need to sort of manipulate my vote to get what I desire. All right, my vote can't be manipulated to get what I desire or to stop what somebody else desires. And that's a better thing. Majority rule with 2 candidates is the only thing. Now, in the next few sections, we're going to look at what happens when we have more than 2 candidates. And that's the real stick. There's going to be lots and lots of methods when we have more than 2 candidates. None of those satisfy the desired properties. Okay. So let's move on to more than 2 candidates, because that's really where the interesting things happen. There's 2 types of voting methods. There's what's called ranked voting, which we'll see later, and then non-ranked voting. We're going to do non-ranked voting first. There's a couple of methods where you can use non-ranked. The most common one, and the one that's most common to us, is probably plurality voting. Plurality voting is kind of like majority voting, or from last time. Every voter gets a single vote, so they're all treated equal. And then they get to vote on a single candidate. Whichever candidate has the most votes wins. This is exactly what we do to elect our representatives in Congress. And also for the state senate. So most of the state voting, state level voting, is this way. You're in your district, so everybody in your district gets a vote. Everybody votes for a single candidate. Whichever candidate has the most votes wins. Okay. Pretty straightforward, right? So if we had this example, for instance, and we have 5 names on the ballot, person A, person B, person C, person D, person E, and they're all running for the same office. C gets the most votes, so C wins, right? C wins. And you might say, yeah, that sounds really fair. And it's kind of fair. It is fair in a sense that it's fair to each candidate. All candidates are treated equal. And it's fair to each voter. Each voter got one vote. Where this becomes sticky is when candidates have similar views. Imagine candidates A and B had almost the same views on every single policy. So if A and B had nearly identical views on the same policy, if one of them were to exit the race, their votes would go to the other candidate, probably. All right, let's just say that in general. And a combined ticket of all the votes for A and all the votes for B would obviously be a winner, right? That overtakes C if we did that. So if we combine these two groups together, let's say A decides to step out of the race and give all of their votes to B, then all of a sudden B wins. Does that make sense? So the advantages of plurality voting is it's really easy to do. It's really easy to count. And it's really easy to understand how it works. Whoever gets the most votes wins. But a disadvantage, the advantage that I was talking about, is that oftentimes when you have pairs of candidates with very similar takes, they often will form a coalition. And then you don't have as many people to choose from. This is one of the critiques of the US system. It's dominated by two parties, Republican and the Democratic Party. And you don't have, when you vote for president, the state vote works on plurality. And there's only two people who have a good chance of winning most years. So we don't get a lot of diversity in our ability to choose who we really want. Okay. Another disadvantage is that the winner might not be Condorcet. Now, Condorcet is just a fancy word for saying the winner might not beat everyone head to head. Maybe B would get a lot of votes if it was just a contest between B and C. Does that make sense? So if it was just a contest between B and C, B might win, but because A and B kind of were split their votes, B doesn't win. So winner might not be Condorcet. And with plurality voting, oftentimes winners can take less than half of the vote. That comes up with Condorcet too, but so it's very possible that the candidate who wins can be supported by less than half of the people. This often happens in really close races. like for state senator or something, you'll see that it's a tight race and that the winner gets like 48% because there's inevitably some people who voted for those third-party candidates. And if a big enough percentage of individuals votes for those third-party candidates, you often get a candidate who wins where they're supported by less than 50% of the vote. Okay. And that's kind of a weird thing to say, hey, my representative is supported by less than half the people in my district. Right? That's a weird thing to say. So those are three disadvantages of plurality voting. And by the way, those disadvantages are not going to go away. Anytime you have lots and lots of candidates, you can create coalitions, diminish diversity. Anytime you have lots and lots of candidates, winners might not be Condorcet. Anytime you have lots and lots of candidates, winners can take less than 50% of the vote. People's top pick. So what we are going to do is we're going to look at a couple of other systems as well that might kind of minimize some of these problems. You can't make them go away, but maybe we can minimize them. Maybe A and B could both run. And if I like the policies of candidates A and B, maybe there's a way I can vote for both of them. All right. Maybe I want to keep as many people on the ballot and not hurt people for having similar views. And that's where approval voting comes in. Now, approval voting is kind of similar to plurality. There's a list of candidates, voter walks in, but instead of just being able to vote for one individual, I can say I approve on individuals A and B, but I disapprove candidate C. Does that make sense? So I can say I am okay with candidate A, I'm okay, I approve of candidate A, I approve of candidate B. And don't approve of candidate C, but I approve of candidate E as well. So the voter gets to approve as many candidates as they want. And the candidate with the most approval votes wins. So you could see in a hypothetical situation where with plurality votes, everybody only got one vote, but there's a lot of people who kind of like A. Maybe A was their second choice. And a lot of people say, yeah, I'm okay with A. And so they got 259 approvals while they only got 54 of the top votes. Does that make sense? And so A would win in that case. Okay. Some of the advantages of approval voting, it's still pretty easy to understand. Still pretty easy to understand. Voters may be more satisfied. Because if I only get to pick my top candidate, if they don't win, I might not be as satisfied. But if I get to pick 3 or 4 individuals, that I like, if one of those wins, I feel pretty satisfied. So there's a bigger chance that I walk away saying, yep, I support the person that actually won. Okay. And it has this other advantage that with plurality, you have to stick out. With approval, you have to get people's approvals. Does that make sense? So it doesn't necessarily pit one candidate versus another. A and B could be really good friends, and they could stay very good friends through the whole process. And A doesn't have to, like, how do I say, diminish B. That's kind of what our system is now. If you watch, politics, a lot of times people will try to say, well, I'm better than this guy's terrible, or this lady's terrible, or whatever. Now, all of the disadvantages still exist. You still might not get Condorcet. You still might not get 50% of people approvals. Even here, you may form coalitions too. A and B may form their coalition and say, hey, vote for us, vote for one of us, but don't vote for C. C is a terrible person. That kind of thing. So you still can do all that stuff, but it's a little bit minimized with approval. Do you think our elections would be different if we had approval voting? Probably would. Approval voting. Approval voting would significantly change the way we do elections in the United States. And I think, and this is just my opinion, we would get vastly different candidates if we did approval voting, especially in the Republican and Democratic Party primaries. Okay. A lot of times in a Republican primary, there's a lot of people with very similar views. In a Democratic primary, there's a lot of people with similar views. And so the one individual who sticks out the most is the person who typically wins the plurality votes. Whereas we don't know if that person really stuck out for the right reason. And moreover, if you're in a Democratic or Republican primary, a lot of times, if person C won by going negative on the other candidates, then the other candidates, will hold bitterness towards person C. If that makes sense. Or that at least the voters for the other candidates might hold a little bit bitterness. So approval voting would probably significantly change our primaries. And we would have probably gotten different candidates in the last few elections had approval voting been in place for primaries rather than plurality vote. It's an interesting thought experiment anyways. Does that work? I'm not saying approval voting is better. I'm not saying approval voting is better or worse. I'm just saying it would probably lead to different candidates. And whether probably lead to maybe less negativity, maybe, I don't know. Maybe. Just different. Any questions about this? Non-ranked voting. So plurality voting is most number one votes, but only the number one counts. Approval is if I like this person, I can give them an approve, but I can give a lot of other candidates an approve as well if I'm a voter. Okay. There you go. All right, I think what I'm gonna do is, I'm gonna wait until next class period for the ranked voting portion. There's gonna be a number of different ranked voting scenarios. That's becoming a popular topic right now, ranked voting. That's happening in a few states and a few municipalities. They did ranked voting in New York City for the last mayor. And yeah, so we'll ranked choice voting. We'll do that ranked choice voting stuff next class. All right? All right, then I will stop here. Remember to complete the homeworks for this week, the apportionment stuff and the bidding methods stuff, and then this voting stuff, that'll be due next week.